We're going to finish out this chapter by taking a look at proof by contraposition. And recall that contrapositive states that if P implies Q, that the contrapositive is not Q implies not P. And remember, these two are logically equivalent. So that means that if the contrapositive is valid, that also means that the original statement is valid. And that's what we're going to do, is we're going to sometimes have to verify and prove the contrapositive, and then show that since the contrapositive is true, then the original statement is true. Let's take a look at a basic example. For all n in the integers, if n squared is odd, then n is also odd. So that means if the perfect square is odd, that means that the root of that, or in other words, whatever number it is that you squared, is also odd. Now that's difficult to prove because we don't have any rules that have anything to do with square roots. But let's use the contrapositive, right? So here's our proof by contraposition. All right, so let's write the contrapositive. And remember, if this is P and this is Q, then not Q would be n is in Z even. And that would imply that n squared is in Z even. All right, so the contrapositive would say for all n in the integers, if n is in Z even, then n squared is in Z even. And that's what we're going to prove, is we're going to prove that contrapositive. All right, so let's start by actually defining some variables. So let's let n, and remember it's saying if n is in Z even. So let's let n be an element of Z even, and n is going to be arbitrary but particular. By definition of even, we know that n is going to be equal to 2k, where k is just some integer. All right. Now we're just going to substitute. All right, so we're just basically doing our direct proof, even though we've taken a contrapositive, and we'll figure that out at the end. Okay, so by substitution, we're going to suggest that n squared is going to be equal to quantity 2k squared. And this is a pretty easy proof to show that 2k squared is going to be even. So that's going to be equal to 4k squared by some exponent rules, which is equal to 2 times 2k squared. And that's just by factoring. And then finally, we can use some closure to get this to be 2p, where p is an element of the integers. Right. And we're done. Now, we've proven the contrapositive, but we haven't proven the original statement. Okay, so thus n squared is equal to 2p and is even by the definition of even. Right. And this is really the only new part, is the contrapositive, which we did up here, and then the ending part. All right, so here's our end part that's a little bit new. We're going to say, since the contrapositive is true, the original statement is true. We can say the original statement is also true. All right, and hence we can say thus for all n in the integers, if n squared is in Z odd, that means that n is also in Z odd, which was, remember, our original statement. Okay, so we proved the contrapositive, and then we went through and we just said that since the contrapositive true, that means that the original statement must be true as well. All right, one more example of using contraposition. If A does not divide BC, then A does not divide B. So once again, this is a clear case where contraposition might be useful for us, since we don't have a definition for does not divide. So let's start this out by writing the contrapositive, right? And if this is Q and this is P, the negation of Q would be A divides B, and the negation of P would be A divides BC. Right? So that's the first thing you have to do, is make sure that you understand what the contrapositive is. And so what we can say is that the contrapositive suggests that for all A, B, and C in the integers, if A divides B, then A divides BC. All right, so that's what we're going to prove. Right? So let's say, so this is just the contrapositive. We haven't defined any variables yet. Okay, so let's let A, B, and C be elements of the integers, and we're going to say that A, B, C are arbitrary but particular. Such that that A divides B, all right? Because remember, it's a conditional statement. So such that A divides B, all right? So remember, if A divides B, so we have to assume that that's true. By definition of divisibility, so by definition of divisibility, we can say that B is equal to AP. Right? Since A divides B, that means A must be a factor of B, so B is equal to AP, and P is an element of the integers. Right? Now we're going to do substitution, and we're going to substitute into BC. Right? And this is pretty easy. This is almost like the transitivity property that we proved as one of our very first divisibility proofs back in section 4. So we're going to say, by substitution, right, we're going to say that BC is going to be equal to A times P, or I'm sorry, A times P times C, right, since B is equal to AP, which is the same thing as A times Q, right, because PC can be closed out as some sort of variable or some integer Q. And notice that P is an integer, C is an integer, so that means P times C has to be an integer, so that means that Q is an integer as well, right? And that's by closure. So there really wasn't much to this proof in terms of algebra and steps, right? So thus, BC is equal to AQ, and hence contains a factor of A, since BC contains a factor of A, this means that A divides BC by definition of divisibility. And we're not done, because all we've done is we've proven the contrapositive. But that doesn't mean that we haven't necessarily made a statement about the original statement. Okay, so here's our final statement. We can say, thus the contrapositive is true. Or we could say, thus the contrapositive of the original statement is true. and hence the original statement must be true as well. All right. So you have to close this out by stating something to the effect of, since the contrapositive is valid, the original statement is valid. Okay, and finally we can say, thus, for all a, b, c in the integers, if a does not divide bc, right, which is what we set up here. So we're just looking back up here. A does not divide bc, then a does not divide a. Or then a does not divide b. All right. So hopefully this gives you an idea as to how to go through and try to prove using both direct proofs for floors and for mods and also for division into cases. And more recently in section 5, we took a look at being able to prove by indirect methods by using contraposition and contradiction.